Good morning, everyone. All right, so continuing on recommender systems, and I found this interesting blog, which was learning to rank is good for your ML career, and I haven't taken a look at much as sort of RecSys for that. So let's see. My plan is to understand this blog and understand basically like for learning to rank. I mean, like you have different approaches, right? So you have like Pointwise, where you sort of independently rate each. Let's say you have a movie, you want to rate movies or you want to give recommendations for movies. Then you could predict the rating for each user for a particular movie, and then you could give them the highest ratings. But let's say that you are giving them 10 movies that they want to watch, like Netflix in a row, then it might not make sense to do that, right? Because maybe all of the highest predicted ratings are very similar and not as diverse. So you would want to give them diverse ratings. And so ideally, you would want to have an approach that can learn to rank in what order you should give them. So that basically your output is a sort of a permutation of your of the ordering that you want to recommend them. So ListNet is what he is talking about in, maybe not in this one, but I think in this one here. Basically, ListNet is one approach that has been proposed in learning to rank, where they went from pairwise approach. So basically, there are like three approaches for ranking. You have the pointwise, you have pairwise, or you have listwise, which gives you sort of a more direct way of giving the recommendations. And so ListNet is one of those approaches for that. I have no idea how it works, so we'll try to. That's sort of the plan for this video. And let me know if you have any. I'll open up the stream, and so if you have any questions, want to chat or anything, then let me know. We'll always pause pause this, and we can always have a chat in the meantime. It's not gonna be that long of a stream, I think. I think maybe hello back from Sweden. All right, let me put this on the side. All right, so learning to rank is good for your ML career. I'm not sure exactly who this is. I just found this. It seemed like a good post. Justin. Background and embeddings. Maybe we can skim this one. I think the part 2 is probably more important. Let's implement ListNet. Probably more important for us. So say that each training example in our dataset belongs to a customer. Say that we have some feature vector for this customer. For our labels, we have an ordered list of products which are ordered by relevance to that customer. How can we go about training a model that learns to rank this list of products in the order described by our labels? Okay, so one thing that's very difficult is that you have these basically you have these so you have like RMSE, which says basically looks at the predicted rating versus the actual rating of a customer or so, and then you have these ranking metrics such as NDCG, normalized discounted cumulative gain, which basically takes into account the rankings or the position of the items in the ranked list. The problem with those types of metrics is that they are not differentiable. So using a gradient-based approach, it's very hard to optimize. So what we want to do is basically try to find a way to circumvent that. So that is what I think the ListNet approach is doing. But this is basically the idea where we want to give them an ordered set. So We must learn to rank. On this epic, in the first post, we'll be describing a motivating example, explore word embeddings. In the second post, we'll be learning about the ListNet model architecture and build a prototype of ListNet on some synthetic data. Cool. And briefly, in the third and final post, I don't think he's done the final post. All right, so briefly describing NDCG as evaluation metric. Much of the following is based on this great paper, a short introduction to learning how to rank. Mm. Okay. Learning to rank refers to machine learning techniques for training the model in a ranking task. Today we're learning how to rank Akash, and specifically about ListNet and from this blog. All right, so describing learning to rank in the context of document retrieval. Yeah, so we have a query and we we present documents. And list ranking, we have F is some ranking, Q is our query, and D is our document. Let's skim this because this is a bit overview, right? We already have like an idea of this. But yeah, basically we have a query, we have a bunch of documents, and we have relevance, grades. We might have multiple arguments for a query with the same relevance grade. For example, a user might deem two to be somewhat relevant. Right, yeah, so we want to give them like let's say this is predicted ratings, then we want to give them the ratings that are the highest for a movie. All right, so they introduce these word embeddings. This is a bit overview. Damn, he really tried to explain everything here. What's an n-gram? And all right. Yeah, we don't have to learn about all of that. All right, so let's go to the second one. Now that we know about word embeddings, let's use them in a model that ranks things. We'll be working through my implementation of a model called ListNet, which was approached in this one. Learning to rank from pairwise approach to listwise. I think this is a really good paper. We should probably take a look at this one as well. All right, so here will be our packages. All right, so basically we're going to give ListNet a query and a bunch of documents to rank. Then, as if through some sorcery, we get a ranked list of documents. So, okay. So like if we use like a pointwise approach, it seems like maybe in general, since it's simpler, with a pointwise approach, maybe it makes sense to, in general, start out with that, and then progressively, add complexity instead of jumping into a directly a list-wise approach. So just something that I thought about here. But so basically, this would be like a query where uh, you give it, what about our, so I guess basically you would give it the entire training, or like your entire movie catalog, uh, and then you would ask, which are the best movies for this user, and this is probably right where the candidate and ranking networks come in, right? Where you need to, because it's very expensive to come up with a complete ordering of all the movies, but maybe you could give it, from 500 you can give an ordering. What magic is involved? Prepare to be disappointed because it ain't too complex. I like that. Outputs are a bunch of real numbers. Each real number is a score assigned to the document we want to rank. We simply sort documents in descending order of score, and this tells us how the original list of documents should be ranked. So you give it to ListNet, you sort it by score, and you get the ranked. Okay, so how does the paper itself? We employ a new learning method for optimizing the listwise function based on top 1 probability with neural network as model and gradient descent. We refer to the method as ListNet. And this is a really old paper, right? This is from 2007, which is pretty a really long time ago, and I wonder if it's still used. I mean, it is Hmm. Okay. So what do they mean by listwise? What is this top one probability? What is the listwise loss function? What is the neural network architecture? So you have these approaches, right? We talked about those, and it approaches it in a more straightforward way because it gives you the directly. It seems like computationally, like like it's computationally expensive to me to do that. So you would probably need to have like a candidate generator to outputs a couple of hundred or so, and then gives that to a ranking one. If you're gonna do a listwise approach. Okay, Pointwise and Pairwise ignore the group structure. So I mean, like in general, I mean, if you look at it from like an overview perspective, obviously you would want to give as much information as possible to the model, and the ordering that you want to output is definitely one of those. So to me, it just makes sense that you would want to do a list-wise optimization. Learning to rank often involves optimizing a surrogate loss function. This is because the loss we want to optimize may be difficult to minimize because it isn't continuous. So this would be NDCG. ListNet allows us to construct our ranking task in such a way that decreasing its loss values more directly impacts our true objective. So yeah, this is basically why we need to do this to circumvent that NDCG is non-differentiable. Where do probabilities fit into ListNet? The author used a probability-based approach to map their lists of scores. Once this is done, they calculate their loss between a predicted probability and a target probability distribution. The authors describe the rationale for defining the problem. We assume that there is an uncertainty in the prediction of ranking lists using the ranking function. In other words, any permutation is assumed to be possible, but different permutations may have different likelihood calculated based on the ranking function. We define the permutation probability so that it has desirable properties for representing the likelihood of a permutation ranking list giving the ranking function. Okay, so basically they use a probability function for their ranking with a permutation probability. Okay. If you're pragmatic, and I'll let you in a secret, the authors end up using the top one probability model, so you can skip the section on permutation probability. However, if you have a burning desire, let's flex those mathematical muscles. Okay, so we have N3 to rank. What are the possible permutations? So we have a bunch of them, right? A lot. And all right, so each denotes the object in a particular permutation. Say that each one of these objects is given a real number, a score, which is used to rank the objects. The authors denote the list of scores associated with each object in the permutation as a bunch of scores. How can we determine the probability of one of the permutations given the ranking function that created these scores? All right, so given that we have the probabilities of the permutations, or we have the scores rather, how do we give a probability to this? So the authors say that this is how you can do that, where you take the product of some function of the score for that particular permutation order divided by the sum, or so you normalize it. I guess these are the probabilities of each. So like the probability that you have this particular score. So we're calculating the probability of some permutation giving a list of score. This is depicted by LHS. LHS of the above. Okay. Walter White. I've always wanted to meet you. Asks, hey, Alden, do you have a full-time job or freelance? I Right now I'm doing like consulting work mostly. Mm, so yeah, but I might be working full time in the future at a company. Hari asks, where to start if you want to learn recommendation system from scratch. Perhaps you can suggest a start point from your place. I don't know the best resources right now. I think, um, yeah, I don't have I think recommender system in general right now feel like it's a bit scattered. It doesn't have that great courses. I'm looking to create a recommender system course or like on YouTube, a playlist. Uh, Basically starting from scratch and implementing the algorithms and building some projects, but that will take some time. So right now, I'm on the process of learning this myself. So uh, yeah, I don't have the best uh, this best way. I think the way to learn is to do what we're doing now. Just take a look at the papers, understand what algorithms, what methods have been used, build them, implement them, try them out on projects, and build some cool projects. I think that's like the overall. So, anyways, like we're predicting here the probability of some permutation. Uh, the big This is capital pi. Okay, so we're doing a product. We have some phi. The only requirement is that it's an increasing and strictly positive function. Okay. The denominator contains a sum. Okay, so what do we get? If we put that specific ordering and we have the scores of each, then we have the probability of permutation. If we calculate the probability of each permutation in our set, we can see that each one is greater than 0 and they sum up to 1. All right, so okay, so like the requirement on the phi function is basically that you're giving a probability, I guess. So then you would do that for each permutation, and you would take uh, the highest one, I guess. That seems very expensive. I don't think that's what they do. The scores sorted in descending order, you have the highest permutation probability. The scores, oh, okay. We make an interesting observation. The scores sorted in descending order have the highest permutation probability. In ascending, have the lowest. Okay. All right. So what is the issue with calculating permutation probability? Yeah, but there's a lot of permutations. Instead, the authors propose another probability model that is based on top one. Okay, so this we can't do this. It would be too expensive. Given some objects we want to rank J, the top one probability for that object is the sum of the permutation probabilities of the permutations where J is ranked first. Okay, so given some objects want to rank, the top one probability for that object is the sum of the permutation probabilities of the permutation where J is ranked first. Okay, the authors then observe that to calculate the top one probability for a given object, one does not need to calculate R permutation probabilities of n objects to rank. The top one is equivalent to this. Okay, so they find some type of, I don't know how they derive that, but maybe we can look at the paper and understand that. But basically, you have this computationally expensive version that where you take all of these permutations, but it's really expensive. So basically, they find a way of hacking to simplify it, and they come up with this top one probability term. Okay, the top one probability is the probability that a particular item is ranked at the top position. It is computed for each item in the list, and the item with the highest top one probability is placed at the top of the ranked list. So basically, you go through each, you predict the top one probability for each, and then you do so it's like a double for loop kind of a thing. Okay, the astute reader may have realized that the formula we used looks like a lot like the softmax. You're correct. Given the way that we wish to define our probability function, we can apply the softmax to our scores and get top one probability for each object to rank. Okay, so you get some probabilities and you simple. We'll convert our relevance grades into probability distributions using the softmax. We'll assign each item an arbitrary relevance grade to illustrate this step. Okay, I'm a little bit lost here because I'm not sure what the relevance grade and the... Okay, so basically you have the relevance grade. From that, you take a softmax, which is the same as the top one probability. And then basically you have an approximation of the true one. And it ranks these two in the incorrect order. Okay, because we have... So like, what's the label here? Like you predict, you give the user like a order of movies to watch, and you want to optimize for some... I guess basically you would have to take into account your specific like the metric you're trying to optimize, and then it tries to change this probability ordering in some way. All right, so I'm a little bit confused here over the true probability distribution and the predicted probability distribution of basically, yeah, like the top one probability, how they come up with that. So they use KL divergence for this, for basically, you know, trying to optimize these probability distributions. yeah, like KL divergence basically just tries to push, we're trying to push these two probability distributions to be the same, and we get some loss from that. Okay, so we now know how to transform our document into probability. We also know how to compare the probability using KL divergence. We haven't covered how we get our scores. This is the neural network. Query doc. Oh, the feature represents a query document pair. Okay, so okay, but then isn't ListNet then built on top? Because you basically get a score for each, and then you give the scores, and it outputs the ordering. Just gonna skim this a little bit. We have a bunch of scores. We need to convert them into probability distributions. All right, so what do you input? You input some documents in a batch, and you have some all right, so you have 5 documents, it seems like. You do some expand batch layer, some dense layers, and then you get scores, basically the scores for each example in the batch and the 5 documents as the output. All right, and so you have a true, you have a predicted one, and then you train it, and then you have true, and you have predicted distribution. All right. Okay, so this is was an overview. Let's maybe go into the paper. I think like it definitely makes sense to do something like this. But I wonder if still a bit confused. Like, okay, so what does these scores mean, and how do you optimize for? I don't know if you want to optimize for like click-through rate or something. Where does that measure come in? Is that the score of it, or because the scores get to convert to probability distributions, right? Maybe we get some answers from this paper. Let's see. Lucas, have you ever considered diving deep into diffusion models, especially implementing their less complex versions from scratch, or discussing research papers in this field? Yeah, I have, but like, I think I haven't. There need to be some like utility to learn it right now. I don't have a specific project in mind or anything specific. Yeah, so like right now, just learning about recommender systems for me, and then uh, like reading some papers in diffusion models for sure, but not like spending a lot of time on implementing them from scratch. Maybe I will probably do that at some point, right? It's the natural extension of like I did a GAN playlist, right? And so diffusion models have taken over GANs a lot, so it would make sense to make a playlist on diffusion models and learning about that, but it takes time. All right, let's take this paper then. Okay, I mean, I've kind of skipped the pairwise approach. I guess it wasn't intermediate to pointwise, but I mean, at least we got an overview here, right? It was a pretty good blog. Just maybe we can go back to this one after checking the paper as well. Okay, so ListNet. All right, so we have feature extraction. For each document, extract a set of features. These features could be based on the content, the query, user behavior data, etc. Score calculation. Use a scoring function, e.g. in your network, to compute a score for each document based on its features. Okay, so I think this would be also specific for each user, right? So maybe you would have a user embedding, you would have you would like basically do like user embedding, item embedding, compute one combined, or sort of the score. Then you do that for each document, and then you do a top one probability. Compute a top one probability for each document using a softmax function over the scores. The top one probability is the most that the particular model document is ranked at the top position. For example, you could rank the movies that a user has watched based on their ratings or watch times. This score represents the model's estimate of the relevance or importance of the movie to the user. Top one is ranked at the top position. I'm really confused actually. Like, where do we optimize? Where do we utilize the user feedback of actual ratings they gave? I mean, this is ridiculous. Come on. I feel like sometimes like this is just annoying, or I don't know. So dumb. Short introduction on learning to rank. We have documents, ranking based on relevance. Maybe this paper is better to look at first. Probably right, because here they actually explain as an overview level, and then maybe we can take a deeper look at the specifics of ListNet. So I guess like basically my question is, I guess it takes some time to find the question, but like in Pointwise approach, you have very clear labels because you know what the user gave that movie. But in list-wise approach, you do not know the perfect ordering to maximize for a specific objective. So how does one train this kind of a model, not knowing the true label? Okay, for example, we might know the user like movie A more than movie B and movie B more than movie C. This gives us the partial ordering of the movies. Then tries to find ordering that is close as possible. The learning algorithm adjusts the parameters of the ranking to make the predicted order close to true ordering. So like how does it know what the true ordering is? That's my question, because we don't know the true ordering. That would be to optimize for a specific. Okay. Okay, let's take a look at this one. So like, what are the questions that what I'm confused about is yeah, like the labels when like if we're using a list-wise approach, how does the labels go into that? Mm,
Um, the
I know he mentioned this, so I just thought maybe it would be good if one could check that.
uh, collaborative filtering examples from into the introduction.
All right, so he talked about learning to rank. No,
And I'll talk about this later, but SBD, the picture that is missing in my slides, interestingly.
here he's talking about deep learning, which is there. So he probably talks about it earlier
Data set that
somewhere.
we're some, and now we're going.
This is when you need Ortus for all
And I'm off
for all
computing
videos.
iterative optimization. We what in the 2000s. So name and -1 limitations and each of the neighbors that thing. Now
I remember he
that's
talked
the
about this,
idea of
but I have no idea where. Like he did mention like the ranking problem. Hi, Riyadh and Jonathan. I guess it must be in the lecture 3+4 maybe. Yeah, okay, it's here. Let's try to listen to this.
And actually, I'll talk about that in a second. The other important thing to understand when you're doing a ranking problem is what is the metric that you want to optimize for. I said before, RMSE is not a good ranking metric. It's not even a ranking metric, right? So we can think about optimizing other metrics like NDCG, mean reciprocal rank, fraction of concordant pairs. Each of these metrics has a different set of properties, and all of them are interesting and good, and you can actually measure your ranking model using all of them. And when I say they have different properties, we usually are interested in how much are they weighting the head of the ranking versus the tail, or what kind of decay do they have in the way they weight the errors you make on the head of the ranking versus the ones you have on the tail. And you can think about, of course, making a mistake on the first position, it's huge, right? So you want to make sure that your ranking metric weights more an error on the first position than an error on the 10th position of the ranking. Now, how much more? That's going to be determined by the ranking metric you use, right? So, for example, fraction of concordant pairs, FCP, is out of the three the flattest one. The other two are kind of heavy on the head. Okay. If we knew how to, and we will get there, we would want to optimize a machine learning model directly to one of these metrics. But these metrics are hard to optimize for, and one of the reasons is they're not differentiable. So if you have a method that is going to be using something like gradient descent, you're kind of stuck with something that is not differentiable. We'll find ways of doing it, but initially, it's not obvious how to do it. So what are the different approaches to learning to rank? The first, easiest one, I already mentioned it, is to treat it as a regular supervised classification problem. And that's really what's called the Pointwise approach to learning to rank, right? So in this case, you basically only need binary judgments on your items, good or bad, right? You just have a class label. And then you use some kind of classification approach. And in theory, you can use any classification approach, as I say here. You're better off if you use a classifier that outputs some sort of probability, like logistic regression. Tree ensembles, like gradient-boosted decision trees, are also very commonly used. SVMs, not so much, because it's not so obvious how to go from the classification of the SVM to the ranking score. But in any case, you can use any classifier as the first approach to a ranker. Any questions to hear? Yes?
If you consider personalization in your supervised learning, what is the true order in your training data set?
Okay, this is exactly my question. What is the true order? Is this?
If you consider personalization in your supervised learning, what is the true order in your training data set?
Yeah, this is like exactly my question. Because like, what is if we're optimizing for learning to rank a list-wise approach, how do we know the true ordering that we're trying to optimize for?
What is your true order?
Yeah. If you consider personalization, what is the person's true order?
I mean, there is, so that's, So it's a good question in the sense that you usually, when you talk about learning to rank in an unpersonalized fashion, when you're doing, for example, search, you construct a ground truth data set, and I think that's what you're referring to, in which you have maybe a panel of experts or people telling you, oh, this is relevant for this query, this is not relevant for this query, right? So in this case, you don't really need such a thing in the sense that you don't have a query, and the query you can think about it is the user, right? So basically, what you're going to be doing is you're going to be constructing a data set in which you have, for this Pointwise approach, for example, you're going to have positives and negatives from a given user, and then you're going to have a value for the features in your model, in our case, popularity and predicted rate.
So this makes sense for the Pointwise, right? Because then we have, let's just say we have their ranking, we give them predicted rankings, and then we ask the model just to predict based on the features of the movie, either collaborative or content-based. But for the list-wise, that's when I'm confused.
Rating, and that's it, right? So basically, think about the matrix of data that you're going to be constructing is basically zeros or ones, whether the user clicked or didn't click on that item, and then the values of the features, which represent the predicted rating for that user, and that's where the personalization comes in, right? So there's not a ground truth data set in the sense that it's equal for everybody. There's a ground truth data set in the sense that you have positives and negatives for each individual user. But those positives and negatives are going to be different for each user, but that's okay, because that's going to be reflected in the fact that the personalized feature, the predicted rating, is going to be different for each user, right? And then the values of the features, which represent the predicted rating for that user, and that's where the personalization comes in, right? So there's not a ground truth data set in the sense that it's equal for everybody. There's a ground truth data set in the sense that you have positives and negatives for each individual user. But those positives and negatives are going to be different for each user, but that's okay, because that's going to be reflected in the fact that the personalized feature, the predicted rating, is going to be different for each user, right? Okay, so moving on from the Pointwise approach, we go to Pairwise. And Pairwise, the idea here is that we're going to be defining the loss function on pairwise preferences. So basically, our goal here is we want to minimize the inversions that we have in our ranking. So we're going to be training models in which we say, well, item A has to be better than item B. And we're going to be optimizing using, again, a binary classification problem, but in this case, optimizing to a pairwise comparison. There are a number of approaches here, and one of them is the ranking version of SVM, rank SVM, rank boost, RankNet, FRank. All of these are pairwise approaches to learning to rank. However, this is not ultimately what we want to do. Oh, guess the battery died. Sorry. Okay. So that's not ultimately what we want to do. I mean, pairwise is a good step forward, but what we really want to do is to do a list-wise optimization. List-wise meaning we want to have the whole catalog of items, and we want to optimize whatever metric we chose, NDCG, fraction of concordant pairs, for the whole list, right? There are different ways to go about it. And the first way is saying, well, given that optimizing those ranking metrics, as we said before, is tough because they're non-differentiable, let's come up with an indirect loss function, right? So, for example, rank cosine uses the similarity between the ranking list and the ground truth as the loss function. And that's indirectly, obviously, related to some of the ranking functions. Or ListNet uses KL divergence in a similar way. and these methods are okay. The only issue, the only problem is that you're not guaranteed that this indirect loss function that you're optimizing is at the same time optimizing your ranking metric, right? But again, it's difficult to optimize directly the other metrics. Okay. So how can we directly optimize those? When I say IR, I mean those ranking measures. So there are actually some genetic programming and optimizing from CLIM come up with different brute force approach to optimizing those with data rank or back. It's really dependent on the kind of data that you have. Many things related to the distribution of your data, and not only your data points or your labels, but actually your feature space, right? And only even for more.
Okay, I felt like that was a little bit. I want to know more about sort of how exactly they.
And learned from with the labeled data, and the learning to rank use this labeled data to learn a global ranking function, and the ranking function gives each item a score, and then give the ranking result according to the score. So we can say that for the learning to rank, existing learning to rank, the scoring process is independent. Let me give an example. Is a supplement to address user preferences and to model to direct the input and followed by a spin.
Calculate the true positive rate for a new item by averaging a scoring function.
Also available. For example, we can attempt some site information respond later. Model-based recall strategy use many deep learning-based models to retrieve items based on the relevance between the user and case adaptive mirror mechanism. Moreover, in the tower, propose the ranking state to optimize multiple tasks such as the MMOE, ESMM, and PLE. Moreover, in addition to the low feature.
So like that paper I took a look at, right? Deep and cross attention paper. Maybe deep and cross. And I wonder if this is a pointwise approach, I would guess. Like the probability that it's being clicked is like the metric they're using at the top, but then you're not taking into consideration the
feature, text, image, and videos
the
are
ordering.
also available in the recommendation scenario. So how to extract the beneficial hidden information from. Compare the ranking with ranking. Ranking is multivariate while ranking is univariate. Besides, for the different ranking model is the supervision signals. For the
All right, let me
user and they like image 1, video 3, image 5.
Would make more sense.
So actually, yeah, so I think here we're pairing a user with a video and looking at how good is that pairing. I just want to run through a couple of other examples in other companies, and then we'll wrap up for today. So Alibaba is also uses something similar. They have a matching. So search, the difference between search
in doing like very good recommendations based on the stuff that you're watching right now. I do use Instagram.
All set. I've got the 5 questions. Are you ready?
I'm ready.
Okay. Thank you so much for joining me and answering some of our questions.
Thank you. Great to be here.
Yeah. Let's start with going back a little bit in time. It's been 20 years since recommender systems started to be introduced in products and companies like Netflix, where you were. How has the field evolved, and are you especially excited about anything in particular?
A lot of things have happened in 20 years. I remember at that time, there was already the feeling that recommender systems were going to have a huge impact on products like Netflix. But I don't think we could anticipate how much they were going to impact products as a whole and even society, if you will. Like, I do remember some people like Chris Anderson wrote a book, The Long Tail, and that was 2008, I think. And he already said we were leaving the age of search and going into the age of recommendations at that time. And I think a lot of people say that's not going to happen. But if you look at what's been happening over the last few years, it's not only that recommendations impact many products, and products like Netflix have over 75% of their actions happening through recommendations. So it's like a huge part of the engagement that happens. But moreover, there's huge, even new products that we could not imagine nowadays happening without the recommender systems, like products like TikTok, Instagram. I mean, they're all based on the idea of there are recommendations. They could not exist without recommendations, right? So I think that's been a huge thing in industry, and it has had a lot of impact even in society, as I'm saying. You were also asking about things that I'm excited. I guess deep learning and the application of things like transformers to recommender systems are very, very exciting, because we're now able to understand content much better than before, which has always been something that it's been tricky. We understood behavior, but not so much content. And now with these new techniques, we can understand content, and we can even generate content, which is like, I think it's going to be the next frontier, not only recommending, but recommending auto-generated content. So that's something that is very exciting.
All right, so I think probably what would be a good thing now, honestly, is just to take a look at some lectures on recommender systems, probably for me, because yeah, I think sometimes it's just good to take a step back and zoom out a little bit and then try to understand the specific papers of learning to rank. But like, to me, it doesn't seem like there's a lot of good lectures for recommender systems.
And this is very typical when you're doing feature engineering into a linear model.
Supervised versus supervised. This is probably a good video just to get some insights into stuff here. So this, like the one I just saw, RecSys playlist.
Supervise versus.
That's the one I wanted to check. I saw it just a while ago and then I accidentally. Is it here? This one, yeah. So this is the one I thought would be interesting. So he has. This is a while ago, right? So, but it can probably still be. Yeah, this is like outdated, right? Probably still things we can learn here, but a bit outdated maybe.
That ontology, or those topics are actually used to classify questions and answers. And then we have more into like restricted Boltzmann machines. The reality is it was won by an ensemble, and not only have, so at the end of the day, it's going to have all those benefits that if you don't have debuggability and you don't know how to react to a bad example.
I think I'm gonna take a listen at this one. I think this is probably
so let
a good thing to listen to. That one, and then probably that one is good. This one might be good to check, like these lectures here, but I feel like they might be a bit outdated. And then those specific papers is probably a good plan.
And that way we can continue to delight all the people.
Industry and academia, I don't know.
Yeah, I agree. I mean, just if you go to different conferences, the fact that there's actually an industry track, that we're actually up here talking about the problems that we have. We're sharing kind of what we see as what we need and think is going to happen in the future. So that kind of, and then being able to share and learn about what's going on in academia on these problems, I think is is great. And so I think it's healthy and can kind of have both sides here and kind of working together.
All right. So plan is take a look at this one, and try to understand a little bit deeper on learning to rank as well as ListNet. I think that would be like a good plan. So that's the goal. I'll be right back.
Okay, so thanks everyone. We're going to get started. I know it's been a long day, and the good news about a tutorial is that we have a lot of time to go more into details and depth that we usually do in some of the other short talks. So I'm Xavier Matrain from Quora and Deepak Agarwal from LinkedIn, and we're going to try to give in this tutorial some perspective on recommenders in the wild in industry and some of the lessons learned. We both have been in this for quite a long time, and we're going to be talking about our experience in our current companies and some of the former ones, like I was in Netflix before, and some of those lessons that we've learned over the years. Also, we both have a research background, so we've published, we've been in academia, and I think we have seen both sides, so we can give you sort of like a good overview of how we think that those things, once you go to industry, they work, and what you need to understand of recommender systems in industry. We're going to have two parts for the tutorial. So the first part, first 45 minutes, Deepak is going to drive it. We're going to have 5 minutes for questions in between. Then I'll take on the second part, and we'll do a joint Q&A at the end. Okay, so with that, I'll hand it over to Deepak. Thanks, everyone.
Thank you. Okay, can everyone hear me okay at the back? Okay, great. Okay, so let's begin. I think most of you know what a recommender system is. So if you don't know this, then probably you're in the wrong room. So again, just briefly, a recommender system recommends items to user to optimize some kind of utility, which is generally composed of one or more objectives. And you'll see some examples as we go through the tutorial. And almost every website today is, or rather should be, powered by a recommender system. So just to give you context, generally this is how the recommender system works. You have a user I who visits the website, and generally you know information about the user. For instance, you know the demographics of the user in some cases. You may know their browse history. You know the location they are coming from. Some cases search history. If you are on a website, generally you have search utility in a website, so you know the search history. If you are on Quora, for instance, you know the topics the user is interested in answering, or the questions that they're interested in answering, and so on and so forth. And then you have an item inventory, depending on the recommender system you are building. Like, you know, if you are in Netflix, you have movies. If you are at Quora, you have answers and questions. If you have LinkedIn, you have jobs, people, and so on and so forth. And again, items also come with features like keywords. In some cases, if it is articles or video, you may have keywords, or you may have extracted information by using computer vision if it's a video, using deep learning technology, which you may have heard in the conference today. You know, sometimes, you know, other metadata like author and all those things are important. So you extract information from the items, and then what the algorithm will do is it's going to recommend the best item to the user. And once you recommend the item, you get some kind of response back from the user. It could be clicks, and again, clicks could be further quantified or qualified as different kinds of actions like share, click, answer, and so on and so forth. Or in some cases, you do not click or do not interact with the item at all, right? And the dilemma here is the usual explore exploit dilemma, which was explained very well in a talk earlier. So should you recommend the item with the highest predicted utility? Or should you recommend an item which is going to help you collect information that's going to make it better for you to recommend things in the future, right? So this is the usual explore exploit dilemma that you have in all recommender system problems. Now, the explore exploit trade-off, the way you solve it depends on a number of factors, right? So one important thing is the dimensionality of your problem. If you have a very high dimensional problem, this could become really bad. And that's where features and metadata help you reduce the dimensionality of the problem to kind of solve it in a proper way. In many cases, the feedback loop is also very important, right? So if the response you get from the user has a big delay, then this problem cannot be solved very well, and you have to kind of apply other techniques and so on and so forth, right? But at the heart of the recommender problem, this is one of the most important things we have to remember. Okay, so today what are we going to do? We are going to talk about recommender systems at two companies. You know, I'm from LinkedIn, so I'm going to talk about LinkedIn. Xavier is going to talk about Quora. And you know, this is the rough agenda. So I'm going to begin with recommender systems at LinkedIn. I'm going to give you an overview. And since this is lessons learned, before we talk to you about lessons learned, we are going to give you some nuts and bolts, flavor of some nuts and bolts of recommender system. And so I'm going to give you some examples from LinkedIn. But again, the concepts which I'm going to talk about generally applies to a lot of problems that you all face in an industrial setting. And then, you know, I'm going to talk about some lessons we learned while building recommender system. And Xavier is going to take over that theme and go in a great deal of depth in the second part. And finally, we are going to conclude. Right? Okay. So let's begin with LinkedIn. So LinkedIn, again, our mission is to connect the world's professionals to make them more productive and successful, right? And right now, there are around 630 million professionals in the world. And by productive, I don't mean just finding a job for you. It's also about making you good at what you do today. Right? So if you are already a data scientist, the goal of LinkedIn is to make you a better data scientist, not like get you another job, not necessarily. And our vision is to create economic opportunity for every member of the global workforce. So the global workforce is much bigger, more than 3.3 billion people on the planet, right? So how would you do that? So I think we have this notion called economic graph. So we believe we can achieve this vision by creating the world's first economic graph. So the nodes of this graph, first of all, are all professionals in the world. And then the companies which they work for, the jobs that are available in these companies, then the skills that are required to get these jobs, the institutions where you can actually go and acquire these skills, and finally knowledge, professional knowledge that can make you better at what you do every day, right? So once you have these nodes, then the goal is, our goal is to facilitate the flow of capital, both of all forms, through this economic graph to make you a successful professional in the world, right? So that's really our vision, right? And before we go into details, like here are some actors and value propositions that we have on the LinkedIn network. So first, of course, we have users. Like any consumer internet company, we have users, and users come to our site to do various things. So they first of all, they come to the site to connect with others in the professional world, right? That is really the heart of every social network. So, you also come to the site to stay informed about the latest that's going on in your area. And sometimes you come to the site to get new opportunities, right? Now, this is where LinkedIn kind of is slightly different from many other companies. We don't just have the consumer arm, we also have the enterprise arm, right? So we also have customers that are also engaging on the site, right? So if you are a recruiter, you may come to the site to hire candidates for job openings you have. If you're a marketeer, you might come to the site to market your products through native ads, for instance. If you are a salesperson, and there are a lot of salespeople on LinkedIn, you may come to the site to reach out to the decision makers in Fortune 500 companies to sell your products, for instance. And in general, if you are a professional, you might come to the site to do your professional job much better on a day-to-day basis by using various tools we provide, right? So this ecosystem where you have members or users and customers coexisting together is what makes LinkedIn unique in some sense, right? And this gives rise to a large number of problems which can be classified as recommender problems according to the definition we kind of started this tutorial with. So for instance, some common recommendation problems that arise as a subscriber, we recommend you courses that you can take to enhance your skills, right? And finally, like if I send you a lot of recommendations through push notification and they're not very relevant, you're going to get annoyed. And these recommendations now, as with every recommendation system, your data is extremely important. So let me give you some flavor of the kind of data we have. Okay, so this is, of course, the first thing is, which is unique about LinkedIn is the profile data, right? So, as you know, we have a lot of semi-structured data about users because we all create accounts on LinkedIn. And by the way, if your profile is not 100% complete, please do so, because that's going to help you get better recommendations, right? So, okay, so, if you look at a typical profile, we have a lot of information about user, their title, seniority, skills, where they went to the school, who endorsed them, who wrote a reference letter for them, what volunteer activities they're involved in, what companies they follow, what articles, what topics they follow, and so on and so forth, right? You can see, like, there's so much information we can have about the user, and that obviously plays a big role in providing good recommendations. In addition to the profile information, as with every usual recommender problem, you look at users' past activity, behavioral attributes, what they have been clicking on, what they have been searching on, and that can give you a behavioral profile as well. We also have network features, so we know citations based on who read the article and so on and so forth. That helps a lot. I mean, there are too many intents on LinkedIn. You figure that out, you just make sure that you're not babysitting the whole thing, right? It could be connection probability, it could be job application probability, and so on and so forth. Once you do that, then you kind of optimize these short-term objectives by using large-scale machine learning. In some cases, machine learning is not enough. You might actually have to change the UI of the app and so on and so forth to kind of obtain optimal results. And then you get feedback from these experiments. You either persist with your short-term proxies or you go back and revise them because what you did not optimize the long-term objective. And in some cases, you might also go and revisit your long-term objectives, right? So you experiment, you learn.
This is all really high level, right? I would like to know, basically like how the models look like and like just go a little bit more in depth.
The following example, which is a job recommendation problem, right? Okay, so what is the objective here, right? So this is the short-term proxy which we have constructed, and that is to predict the probability that a user I is going to apply for a job J, right? And again, what is the information you have at your disposal? You have all the user features which I talked about earlier. You can obtain a lot of features for every job, right? As we talked about earlier. You also have data about users' past interaction with different kinds of items, right? And this is how the high-level system.
So you have a user that interacts with the front end that has user activity data streams, user feature pipelines, store those features. You have a ranking service. This is the online stuff. Live index updater. Okay, so you have an offline index builder. I guess this is, what is he talking about here? Is he talking about sort of the feed, I guess?
For every job, model training pipelines. The system architecture looks like. So let me go a little slow. So this is a very high level overview of the system architecture. So at the heart of this is, of course, the model training pipelines, right? Machine learning model training pipelines. And we have a system called Photon internally. And so the beauty here is every single person who wants to build a model uses exactly the same workflows, right? So there is a nice template, and if you want to build a machine learning model, you can easily do that by using this template and workflow. So that's the model training pipeline. Now, you cannot train models unless you have data. So of course, you have to collect data. So how do we collect data? So when a user comes to the site and interacts, we collect data, and we heavily use Kafka. So Kafka is something we use internally that was invented at LinkedIn, but I think this is a very popular open source as well for messaging system, which many of us use in the industry. Now, once you collect data from a user, we have a feature processing pipeline, right? So there are two kinds of feature processing we do. There are some feature processing that happens in near real time. So for instance, if a new job gets ingested into our pipeline, we immediately trigger some jobs to extract features for that particular job, right? So that is done through stream processing, and we use Samza for doing that, but you can use other things as well, like Storm and all that stuff, right? If you as a user go to your profile and change, suppose you got a new job and you change your profile, we want to immediately process that data and kind of add it to your profile, because maybe someone is going to search for you 5 minutes from now, and we want to make sure we show them the updated information on your profile. So there are some feature processing that has to be near real time, and for that we use stream processing. There are other feature processing that need not be near real time, and that we do at the end of the day by using Hadoop, right? So the data goes into Hadoop, and then on Hadoop we kind of create those features because it's not very time sensitive, right? So this is about feature processing. Then, of course, we need a key value, distributed key value store to store these features. So for users, we use Voldemort's, but you can use HBase if you want, right? You can use Cassandra, for instance, right? So these are user features that we construct. Again, some examples of user features could be the profile features I talked about. Some examples could be even matrix factorization, right? So you look at user and look at how they interact with different kinds of articles, and then you create a latent factor, and you want to push it so that you can use it at runtime, right? So all kinds of user features and model coefficients, they all stored in Voldemort. Now for items, it's a different story, right? Because if you have a very large item set, you want to be able to retrieve these things very quickly at runtime. And so that's why we have something like a Galeen. We have an internal system called Galeen, which is enhancement of Lucene, right? So this system helps you retrieve items very quickly by using posting list, inverted index, and so on and so forth, all that nice stuff. And here too, we have two different components. One is the offline index. So the offline index gets updated every day or every week. But there is also a near real-time component that gets updated as soon as the item gets ingested into the system, okay? And then finally, we have the ranking service, right? So whenever a user comes in, the ranking service will call the user feature store. It will get the user features. It will get the models. It will get the item index. It will get the items from the item index. And then it's going to do computation at runtime and show the best items. OK, so and once you have done that, of course, you want to do experimentation, right? So you need an A/B testing platform. Whenever you're doing a change to your model, you want to run an A/B test and see whether it's working or not. And here, too, we have a single experimentation platform to do all experiments in the company, right? So let me give you an example of feature generation, right? Since this is so important to scalability, right? So, so we have all kinds of features, but let me give you an example. So in this case, what we are trying to do is as soon as a job gets ingested into our system, we want to extract the skills that are necessary to get that job in near real time, right? That's really what we're trying to do here. So a new job comes in, and that triggers a SAMHSA. There is a list.
It's really interesting, like listening to how these things work, right? For example, learning about how ad prediction works, or how YouTube recommender system works, or Netflix recommendations or LinkedIn recommendations. It's really interesting because you fundamentally like view everything a little bit differently. So
Listener,
it's
so there is a
interesting to learn
listener that
about
is
for
listening
sure.
at some port, and as soon as the job comes in, there is a change event that gets triggered in the system, and the listener wakes up, the job wakes up, and it starts processing this job, right? And again, there's a DAG of computation, predefined computation that is already defined, and what this, sometimes this DAG may require some metadata that is available from some database, right? So in this case, there is a machine learning model that tries to predict whether a job J requires skill S based on job description and all that other stuff, okay? So you extract the data from the job, and then you transmit it through Kafka, and the Kafka pushes the data into the live index, and it also pushes the data into Hadoop, which kind of gets into the base index for further use, right? So this is, and then this is something that can be used by everybody in the company, right? We don't want every team to be extracting the same thing repeatedly, right? We do it once, and then everybody uses the same thing, right? Okay, so now model training. How do we do scalable model training? So as I said, we use this system called Photon ML, but this is again something that I'm sure
A lot of engineering work to do this. This is I'm like directly a cyclic graph of transformers. Just a little bit confusing because this is
items,
2016.
and you also have unknown parameters. So I might actually change his expressions. Okay. So as I was similarly ranking ID, as soon as it gets the user ID, it can do pipeline index more. So in this case, for instance, you ran an experiment, and you can get the impact that experiment had on a lot of metrics, I guess. And the goal of the LinkedIn feed, the primary goal of the LinkedIn feed, is to make sure every user is connected with the network, right? So you connect with people, but then you need to nurture those relationships. You're actually looking for kinds of things to the users all at once. So normalized, you can see that the overall reduces with every repeat exposure. And that happens here as well. But the interesting thing here is different types have different decay rates when you're actually repeatedly exposed to the article. Or so if you're repeatedly exposed to the article versus exposed to the ad, the rate of decay is different. Okay. Diversification. So what I'm showing you here is if you show two adjacent group discussions to the user on the same page view, the click-through rate reduces by 20. You need to see them in three. And finally, how do you combine these different objectives, right? There is one objective which is to increase engagement with the feed, but at the same time, you also want to increase your ad revenue, right? So how do you balance both these things? Because they're competing objectives. If one goes up, the other goes down, right? If they were all in the same direction, then there will be no problem. So this requires some constrained optimization, and this is how we kind of formulate the problem. We want to maximize revenue, but subject to constraint on how much engagement you're going to lose to do that, right? And a simple solution is a simple solution entails using a linear combinations of what we call in ECPI, expected cost per click, as it's called in advertising, plus some constant times the click-through rate on the feed. And that constant SB, I've used SB because we call it shadow bid. So think of shadow bid as the intrinsic valuation that organic content has for LinkedIn itself, right? And as you vary that constant, you can actually more liquidity in the entire ecosystem as a by encouraging people who are, right? And that there is a blending layer which kind of rank orders all these top Ks into a single list by using, it's a very simplified, the flavor of plug and play. We do things both from a scalability perspective and, hopefully the feed example showed, although we have nice components that people can plug and play with, every problem is different, and every problem is nuanced, and you have to kind of know how to put these Lego pieces together for each problem. There's a lot of creativity involved in solving any particular problem, even though you have the Lego pieces at your disposal to kind of do things properly, right? So with that, I'm going to talk about some of the lessons which we have learned in building these things, and I think Javier is going to continue with a lot more. But let me, again, this is a theme that was also raised in many talks before, cost of a bad recommendation, right? We all know about explore, exploit, but cost of exploration is something that has to be carefully considered in the formulation. Sometimes cost of exploration can be really hard, and although that's a concocted example, and I being a PhD in machine learning, I'm still offended at that recommendation, right? So people exploration can about where is going to explore, exploit, but cost of exploration is something that has to be carefully considered in the formulation. Sometimes cost of exploration can be really hard, and although that's a concocted example, and I being a PhD in machine learning, I'm still offended at that recommendation, right? So people react very emotionally when there is a bad job recommendation, more emotionally than maybe a bad movie recommendation, I don't know, right? So you have to keep these things in mind. In some cases, like if you're showing puzzles on the feed, even the best of my friends actually interact with it, and the click-through rates go through the roof. But we do not want to promote these things on LinkedIn because LinkedIn is not Facebook, right? And so sometimes having a clear product focus also helps, right? You want to have a professional feed, and no matter whether content is engaging or not, if it is not professional, you should filter it out, right? Otherwise, in the long term, you lose your brand, right? You lose what the product is meant to do, right? We have also found that sometimes providing better insights and explanation that go along with your recommendation helps the user build trust. But it's a very, I think this is an area which needs a lot more research than what we have done right now. And there were some talks on that as well in the morning. Finally, data tracking, right? We can build the most fanciest machine learning model in the world, but if the data is not good, garbage in, garbage out, right? And so how do you make sure that you're tracking data in a consistent way, and you're monitoring the quality of data? That's extremely challenging, right? And it's scientific, then what comes, right? Technology on LinkedIn. And this is some clicked on, he shared it, right?
How do you handle one that's
one day that you change, so you can we'll
to what you reached building this session. As 10 minutes
as much as
for joint Q&A at the end. So if you have more questions, just save them for the end. And I'm going to get started. And as Deepak said, I'm going to be talking very briefly about recommendations at Quora. I actually don't want to spoil. We have another talk tomorrow in the industry session, and Lei Yang is going to be talking about this. So I'm just going to very briefly talk about recommendations at Quora, and then I'm going to continue talking about some lessons learned from building this real-life recommendation systems at scale. Okay, so, but just to get a sense of, especially because I'm going to be using some examples from Quora, the first thing that I want to highlight is the mission that we have at Quora, because as Deepak said, if you don't have a goal that is sort of like high level, then everything else you're going to do by trying to optimize your metrics doesn't make any sense, because you have to build those metrics according to what you really want to do with your product and your company. So in our case, our goal is to share and grow the world's knowledge. And of course, now we need to go into defining what knowledge is and how do we do that. But as a result of that, we use the paradigm of question answering to grow knowledge, which is different, for example, than the encyclopedic approach that building Wikipedia uses. And that's why we get millions of questions and answers and users and thousands of topics. I'm going to ask the same question that Deepak asked. How many of you are Quora users? See, okay, a little bit, maybe over half, so we're getting there. So what we really care about, and then now going a step down below the mission, things that we care about, and then we're going to turn into metrics and into algorithms, are three things. So we care about relevance, and that's a typical thing that recommendation systems care about. They care about how relevant this is for a user. We also care about demand, like generally how many people want to know this knowledge in the world, right? If it's only you, maybe we don't need to put so much effort if it's something that a lot of people want to know about and it's knowledge that people want. And then very importantly, we care about quality. So all the other two don't make any sense because, as a matter of fact, one of the definitions of knowledge is that it needs to have at least a threshold of quality. Otherwise, it's not going to be. It's going to be information or noise, but it's not going to be knowledge. So, as many of you know, Quora is mostly textual based. We have questions and answers, and we have a lot of text. And we've done some interesting analysis. If you go to the data block at Quora, you'll see, like, for example, this one about discussions over time, some of them related to topics like politics and how they evolve and how they change over time. And in this particular case, we were focusing on the term Obama over some months. So we do have a lot of text, but the interesting thing is we have a lot more things than text. And this is a diagram that I used to talk about the different data types that we have and how they connect to each other. And one way to think about it is we really have the overlay of different kinds of graphs, right? So we do have a social network because we have users that connect to users actually in different ways. They connect to users by following, but also by endorsing. We also have a topical network because we have topics and we have kind of an ontology that defines topics, and that ontology, those topics are actually used to classify questions and answers. And then we have the relation between the content itself, between the questions and the answers, and the connections between all those different overlays, right? So users can answer a question, they can upvote an answer, they can upvote a question. So the bottom line is we have a lot of very different data types, and all of those can be used to recommend different things at different times. And again, Lei is going to.
Like, this is really interesting, but it's quite specific, right? To like every case is different, right? So I mean, it is going to be specific, but it's a lot specific to like LinkedIn and Quora, and it's sort of general stuff, right? Maybe it's better for us like to dive a little bit deeper on specifically learning to rank paper. So this one, short introduction to learning to rank, and then ListNet, I think would probably be most beneficial. I'll just get glasses and then we can read it. All right, so I think like this is a challenging topic, and we might not understand it completely, and you might have to take it in several sort of passes, right? But we have an overview, so let's try to just understanding it and see what we can learn from it. I think this is a very important topic to understand, like learning to rank obviously is a fundamental topic. So all right, learning to rank refers to machine learning techniques for training the model in a ranking task. Yeah, I mean, we already have like an understanding of this. Okay, so let's see. We aim to train a local ranking model that can assign a score to a given query document pair or equivalent to a given feature vector. Oh, the local ranking model outputs a single score, while the global ranking model outputs a list of scores. Currently, there are two ways to create training data. The first one is by human judgment, and the second is by derivation from search log data. Okay, I mean, the first approach makes sense. I don't think the human like label thing makes too much sense. We formalize learning to rank as a supervised learning task. Suppose that X is the input space consisting of a list of feature vectors, and Y is the output space consisting of lists of grades. So this is like the first problem, right? Okay, I mean, the learning to rank makes sense if you have like human labeled orders of what's the best for a specific query. And so you can easily do that then, but how do you do it when you're doing sort of movie recommendations is not too clear. I mean, for example, you can get information on, the user clicked movie 3 first in that list. So problem item 3 should be first, but how that gets incorporated in the formulation is not clear. So that is sort of a question I have, and hopefully we will get answers to that. See, further, suppose that X is an element of X representing a list of feature vectors, and Y is an element of Y representing a list of grades. Let Pxy be an unknown joint probability where random variables X takes X as its value and random variable Y takes Y as its value. Assume that F is a function mapping from a list of feature vectors to a list of scores. The goal of the learning task is to learn a function giving training data. Yeah, okay. Okay, so that's like an overview, I guess. And then you have the pointwise approach. It's transformed to a regression task or classification. And then the group structure rank is ignored. Yeah, the group structure of ranking is ignored in this approach. In the pairwise approach, ranking is transformed into pairwise classification or pairwise regression. In the former case, a classifier for classifying the ranking order of the documents is employed in the ranking of documents. In the pairwise approach, the group structure of ranking is also ignored. Yeah, I'm not sure exactly like how the pairwise approach does it. So the pairwise approach would I feel like these should be pretty, I mean, this should be like, it's difficult. Like, I think sometimes when you're confused over stuff, knowing what to ask is more difficult than like knowing what to prompt. Knowing what to ask is the difficult thing. So, I mean, it's no doubt that GPT-4 has the answers to these. It's like, maybe we can just, can you explain pairwise versus listwise approach for ranking system? So once the model training can be used to rank a list of items, this is by comparing all pairs of items. Isn't this okay? So I mean, yeah, we know about this. Like it predicts a score for each item, but what does the score signify? All right, so it does this end to end in some way, right? But then how does oh, this is too general. So let's say for let's I think a concrete example would be beneficial. Let's say our model currently gives a movie ordering. How do we then capture user feedback to retrain? Okay, user feedback. It watches the first, third, and fifth, 5, 3, 4 ground truth rankings. Based on the user's ranking, we can create a ground truth ranking of the movies the user watched. In this case, the first movie would be ranked first. the fifth movie second, and the okay, so from those we create a ground truth. Okay. Okay, so then we retrain. We can now use this ground truth ranking to retrain the model. We input the features of the movies. So the question is then, okay, I mean, that makes sense, right? But then how does it train? So okay. Okay, so that makes sense. Actually, makes more sense now. And the way we set this, right? This depends on the feedback we use. We might have some specific formula we've computed, based on heuristics of watch time or something, if we have implicit feedback. And then we just recompute based on that the ordering of what we want to give. So that makes sense, I would say. So the question is then, like, how does this ListNet work? And specifically, I am confused about the permutation probability and how they came up with top one probability, and why that makes sense. Top one probability is proportional to the exponential of the score divided by the sum. This is essentially a softmax. Loss function then defines a loss function based on the difference between the predicted top one probabilities and the ground truth. The ground truth are usually determined based on the relevance judgment. Relevance judgment, cross entropy, which is a common measure of the difference. Okay. I feel like we're slowly getting a little bit more understanding there. Which is good. Let's see, is there something that let's see, can you go through in depth of ListNet approach works and the derivation from going over how we want to know how we go from preferred order as to actual probability distribution, which is what ListNet optimizes. Okay, the predicted distribution would be created in a similar based on the scores, but we assign, okay, and let's say we would instead use the explicit feedback of rating movie 1 through 3 and 5, was it? And give them okay, well, at least we have an idea, right? Okay, so let's go back to this. All right, we have a listwise approach, and I don't know if I want to go into all these different ones, right? They are a little bit maybe too complex, unless he mentions ListNet here. But this is basically the summary, right? We have this these three different ways of doing it. So learning to rank from pairwise approach to listwise approach. The paper is concerned with learning to rank, which is to construct a model or a function for ranking objects. Learning to rank is useful for document retrieval, collaborative filtering, and many other applications. Several methods have been proposed, which we take object pairs as instances. We refer to them as a pairwise approach in this paper. Although the pairwise approach offers advantages, it ignores the fact that ranking is a prediction task on list of objects. The paper postulates that learning to rank should adopt the listwise approach, in which lists of objects are used as instances. And yeah, I think this makes sense, right? The paper proposes a new probabilistic method for the approach. Specifically, it introduces two probability models, respectively referred to as permutation probability and top one probability, to define a listwise loss function for learning. Experimental results on information retrieval showed that proposed listwise performs better than a pairwise approach. So I guess the question also here is um, Okay, so let's assume we um, so this is what I would like to do also. So I would like to take the movie lens data set. We start with, the absolute simplest. We take just a popularity based, and then maybe you would take like a memory based collaborative filtering. So we would check, just from the interaction matrix, we would check, where did they what is the average for, what are the closest users, what have they watched, or sort of an item based approach, and then do yeah, like content based. The next it could be content based. Maybe that would be one idea too. But let's see, the collaborative filtering, matrix factorization for sure, and then one could try, deep learning or something. Because this is what I'm thinking is like really good to try to understand these things from scratch and just like build them, and to do it on a specific data set. Okay, so that would probably be interesting, right? To learn about. Let's go back to this because I still want to understand the ListNet approach. The paper postulated learn to rank, right? We did that introduction. So let's skim this a little bit first. Central issue of many are ranking. It has brought attention because there are many advantages. There are advantages with taking the pairwise approach. Existing methodologies and classification can be directly applied because we know which one was preferred, maybe. And yeah, okay. In the pros employing what we call the listwise approach. So was this the first, I guess? We propose a probabilities that calculate listwise loss function. We applied ListNet to document routing and compared results of existing pairwise methods, including ranking SVM, RankBoost, and RankNet. The results in 3 data sets show that our method outperforms existing I guess like one thing that is better maybe with like a pairwise ranking is that you have a lot more training labels, right? Mm. So like I guess like rank list-wise is potentially overfitting issues, and you need to be careful with regularization and so on. Okay. The major contributions are: 1, proposal of the listwise approach, formulation of the listwise loss function, development of the ListNet method, empirical verification. Section 2 introduces related work. Section 3 general description. So let's do that. Listwise approach. In this section, we give a general description. In training, we have a set of queries. Each query is associated with a list of document. Furthermore, each list of documents is associated with a list of judgment scores, where Yij denotes the judgment of document Di based on a query, J with respect to query Qi. Okay. The judgment represents the relevance degree of a document to a query and can be a score explicitly or implicitly given by humans. For example, Yi can be number of clicks where the document is retrieved and returned for a query at a search engine. Okay, so that's what we talked about, right? Or when we asked GPT, is that we have basically it can be this implicit feedback, right? The number of clicks, so that if for a specific ordering, the number of clicks are higher for a specific one, that gives that it should be rated higher, maybe, or ranked higher rather. The assumption is that higher click on rate is observed for Dij, the stronger relevance exists between them. I mean, that makes sense. A feature vector is created from each query document. Oh, a feature vector X is created from each query document pair. Okay, so basically that is like, that would be a feature vector for each user item. I guess. So we have like for each user item. So we have, okay, I'm not sure how that, because I'm thinking like the model would give, like you would be giving a user and you would want to get just the top recommendations in the order, in the ranked order for that user, for what movies they like to watch, for example. But here you would have is created from each query document pair. So it's for a specific query. But like for movie recommendations, I guess you wouldn't have a query. So it could just be the user. All right, anyways, each list of features and the corresponding list of scores then form an instance. We can then create a ranking function for each feature vector. It outputs a score. For each feature vector, it outputs a score. For the list of feature vectors, so I wonder if like does it do this independently, because then it's like 2 steps, but you know, it's saying that it's in one single step, so then it would take all those feature vectors at the same time and then output them, I guess. That would be a lot though. The objective of learning is formalized as a minimization of the total losses with respect to the training data. In ranking, when a new query and associated documents are given, we construct feature vectors from them and we use the trained ranking function to assign scores. Finally, we rank the documents in descending order of the scores. We call the learning problem described above as the listwise approach to learning to rank. So I guess, you know, this would be, you know, if at least you're given a few documents to rank, then it's possible to do this all at the same time. Like if you would always get 50 or something, but if you would be getting, you know, 5 million, then it might be a problem, right? So this does not scale. By contrast, in the pairwise approach, yeah, okay, we already know about that. We propose using probability models to calculate the listwise loss function. Okay, we suppose permutation probability. All right, so then you multiply them. Okay, they have some theorems. They have top 1 probability. Okay. Then you have ListNet. So you have a bunch of training data, which is X, which is the, oh, okay. So the training data here is X, is the feature vector of, let's say, movies. So it would be the feature vector for each movie. No, wait, what is the training data here? Okay, I mean, the idea was, right, we have a feature vector and we want to give a ranked order. So Y here would be, I guess, a vector of the, okay, I'm a little bit confused actually what those are. Let's figure that out a little bit later. But then we have number of iterations, learning rate, and then we iterate. And then for each training example, we input xi of query qi to a neural network and compute score list zi. So we compute a score list and then we update, okay. Using equation 3. There we go, okay. So this is, okay. This is the predicted scores and these are the actual scores, and this is like the KL divergence or something, I think. Basically, I guess we're trying to push these two probability distributions closer to each other, and this is the metric by like how we do so. We compared the ranking accuracies. Okay, let's see. Actually, I'm curious how much better it is. Okay, so you have algorithms. You have ListNet as the blue one, RankNet, rank SVM and rank boost. I would be curious to know, what a Pointwise does as well. But yeah, okay. So I mean, like it's. What is 1, 2, 3, 4, 5 here? At n. Okay, right. It's depending on, I guess, the number we're looking at. All right. Okay. So what are the actual like questions we have? I am. Wait. Let's see. One sec. All right. So like the actual question is. Okay, we get that like the labels are taken from like implicit feedback of how the user interacted with the items in the ranked order that we gave them, depending on what metric we use. Let's say we use the number of clicks that as they said. Then those are the labels associated with the probability distribution, right? So like if we have 1,000 clicks, the third one is clicked a lot more than the other ones, then the third one should be ranked highest, right? I guess that makes a lot of sense. And so we give information on like, because like how things are clicked might depend on the, first of all, like the ordering itself, but also the items in the order. So then the network can learn about that, which is good. It gives it more context and more information. But what I am confused about is the feature extraction of, let's say we have for movies. How would it look in the case of movies? All right, so maybe we can, let's say we are building approach for movie recommendations. So we want how. So scores and how to retrain. So gather data on the number of clicks each movie has received. Normalize click data. I don't know. A feature vector x ij is created from each query document pair. So we have one query, and we have for each query we have a document set, and then we have each list of features where we have basically let's see, like a feature. Oh, okay, so we have each list of features xi is a list. So is this like one value, I guess? This is for a query qi. So basically you would get one set of features for all of the documents in the query. Okay, so it would be, so is this one vector? Okay, so this is itself one vector, a feature vector, because this is like one. Okay, so this is a matrix, I would guess. This is a list of feature vectors, I guess, is my interpretation. And then you have a list of scores. So you have a feature vector here of the query in that document. So that would be, you know, for movies, that would be as well. So it really seems like two steps to me, though. They mentioned, you know, that they do it sort of end-to-end fashion, but it definitely seems like it's more of a split. Let's go back to the blog post and see what he says. All right, so we have 3 objects to rank. We have bunch possible permutations. So each of these objects is given a real number, a score by our model, which can be used to rank the object. I'm confused, man. Let's see if we can find someone explaining this in a video or something.
Hi, thanks for hanging out so late on a Saturday night. I know there's lots of other things you could be doing in Brno or at this conference, so I appreciate you turning up. So today I want to talk to you about learning to rank. So raise your hand if you've ever used a search engine and not found what you're looking for within the first few items returned. Okay, and then perhaps you go on and you amend that query, and all of a sudden the results get even worse. And next thing you know, you find yourself clicking on that dreaded button to take you to the second page of Google. So contemporary search engines are often good at finding all of the results for a given query, but less good at identifying which ones are the best and thus should be returned first. And search engines are everywhere. We're not just talking about Google and Bing here. They're just a subset of the bigger class of search. So looking at this sample of places where you'd find search, you can see that good search functionality is going to lead to happy customers, better business revenue, and so the task of ranking documents quickly and accurately is very important. It was at a conference last year when I first started learning about learning to rank, and from there I've just gone on to learn a little more. Today I want to introduce the topic to you. I'll tell you the things that I learned about, and I'll point you to the resources that you need in order to get started and implement these algorithms in practice. We'll look at the standard machine learning algorithms for learning to rank, and we'll look at implementing the algorithms in Python, specifically using the XGBoost module. To begin with, we're going to outline the problem at hand so that we're all on the same page. So the first thing we have is a query. I'm assuming that this query is text-based, so it's going to be the phrase or the words that you type into the search box. It might be, in the Netflix case, Christmas films or Christmas films starring Hugh Grant. Everyone happy? Sweet. In addition to the query, we've also got our set of documents. So each document might be a film title, a blurb, an abstract, a list of actors. It might be a web page, or it might be a standard issue document. There's likely to be some sort of structure in that document, so I'm assuming that it's got a title, a subtitle, and it's probably comprised of sections. There's also likely to be some data-specific structure in there, so if we're thinking about web pages, I'd probably count the URL as part of the document, so I'm using this term quite generally. The goal of learning to rank is, unsurprisingly, to rank the set of documents. Any learning to rank algorithm aims to return, for a given query, the set of relevant documents in order from best to worst. So an age-old method for learning to rank would be full text search in a database. So in this case, your documents would probably live in a Postgres database. And as we mentioned, they've got this fixed structure, title, subtitle, paragraphs, and so on. So full Postgres text search looks at where within the document the terms in the query are. So here I've circled them, and then that is used to rank documents from best to worst. Something that's nice about Postgres full text search is that the user can do some tuning. So if you know, for example, that in your case, the words in the query appearing in the subtitle is for some reason more important than the words appearing in the title, you can indicate that. But that's going to have to be done on a query-by-query basis, and it's going to need some human intervention there. So it's fine for some examples, but it's not really going to work on large databases or more complex queries. Another standard ranking algorithm is PageRank. So PageRank is great for many things, and sadly, it often downweights pages that have few URLs in them, few hyperlinks, and so on. The algorithm also uses wisdom of groups, wisdom of crowds, to learn and to make improvements. And I think we can all think of recent examples of where wisdom of crowds is not a good thing, and a crowd making a bad decision leads to more people making a bad decision. So what we really want is for an algorithm to be general, we want it to be robust, and we want it to not need any query-specific tuning. So that's why we're going to need to think about machine learning techniques in this case. All of the machine learning techniques begin the same way. For a given query document pair, they try to capture the overlap between those two. So this is done by making a feature vector. A feature vector is a numeric vector of values that holds information about those two items. So how do we get this feature vector? Well, there's going to be some features that depend on the query and the document. So these are known as query dependent. They might be things such as how many words in the query appear in the document, how far into the document do we have to count before we hit a word in a query, and so on. And there's a nice statistic known as IDF, or inverse document frequency, which is often used to measure these kind of things, how often words appear in different parts of the document. We've then got some query-independent features, depending only on the document. So these are things like the length of the document, the number of times any user has accessed that document, or the number of hyperlinks in the document. So for different applications, some or all of these features may be relevant. The final set of features are query-level features. These are things like length of the query, and they depend just on the query themselves. So actually deciding what to put in these feature vectors is a very hard problem, and could be 10 different talks. So for the purpose of this talk, I hope we can all just assume that we have a nice feature vector that holds this information, and we are good to go. Once we have our set of queries and documents, and we've made our feature vectors, we're nearly ready to learn to rank. All that's missing is a score, which captures the relevance of that document for that query. So this score is going to be user imputed, so we're sadly going to need somebody to go through the set of potential training, query, and features that we have and rate how good each of these items are. So this is a supervised machine learning technique. There are some ways to compute those scores on the fly, but we're assuming that someone has gone through and given us a training set and said, hey, this document is good for this query, this one is not, and so on. So the first class of ranking algorithms I want to talk about are Pointwise ranking algorithms. So they work by taking each document one by one, and using the feature vector for that query document pair, they go on to predict a relevance score. They predict how relevant that document is for that query. Once this has been repeated over all the documents, we're able to order the documents by their predicted relevance from best to worst. Thus, we have our ranking, and we're done. So the missing piece of this puzzle is the model, which is a function that takes us from that feature vector and takes us to the score or relevance. So for the purpose of this first illustration, I've just simplified and assumed that we've only got one feature in this case, but you can imagine this is multidimensional. Now, we don't know what the best function, our model, will look like, but we don't have to. So machine learning is the process of automatically generating the function given heaps of examples. And there are many machine learning techniques, and arguably the simplest involves learning a way to add and multiply these features together to give us a relevance score. So you may remember linear regression from a statistics class, and that's all we're doing here. Linear regression, in this case, is giving us a model and a way to turn our features into a relevance score. And we also have a way to evaluate the quality of the model. So we could compare for the features where somebody has gone through and given us the true score. We can compare the prediction that we get from this model to the truth that was given. So once we have our model, we can then take in a new feature, pass it into the model, and get a score. There's lots of other ways we could have learned this function. So we could get a different model by learning a curve, and I'm sure you can think of your favorite regression type to give you a different model. given that there are a few possible models, how do we compare them? Well, since we're working with a training set where some human has given us the true score, we can just compute the difference between the truth and the prediction. That gives us a way to evaluate our model. So that's fine, but that only really captures part of the picture, because what we don't care about is the scores. When you go into Google, you never see those scores returned to you, right? All we really care about is the order of the documents. So here we're going to look at an alternative distance metric we could use, which takes into account the ordering of the documents rather than the score. So to begin, we take the predicted scores that were given, and we use those to rank the documents. I'm then going to replace the scores with the rank. So the item on the left becomes rank 1 because it was ranked the best. The next one down is 2, next one down is...
So we've gone from sort of the Pointwise to the like this is yeah, like the true rank here would be based on like number of clicks or something. And so the question is, how do we utilize this ordering to retrain and get better for the next one?
Down is 3, and so on. Now, we know the truth in this case because those scores have been given to us. And so I put the truth underneath. And this distance metric is just going to be how many permutations do we need to make in order to get the true rank in order.
Okay, so this is pairwise, I guess. Like, how many swaps do we need to make to take this, you know, the predicted rankings to the true ranking order? And so we can do that using the pairwise, which was a, you know, RankNet or whatever.
So we're going to go from that top line being in order to the bottom line being in order. 1, 2, 3, right? So our distance metric under this distance is 3. So we've seen 2 different ways of evaluating the model now. One looked at the scores, and one just looked at the order of the returned documents.
So the question is like, okay, I mean, so that is pointwise to pairwise, but then my question is like, how do you compute the scores? Because, I mean, like you, even in the listwise or the pairwise, I guess in the pairwise might be slightly different, but you would need to compute some score in that as well. So in the listwise, how do you get, yeah, like how do you train for the scores?
There are 2 things I want to call out.
And also maybe you have data where you know individual rankings, but you also know the rank, the group ordering sort of true labels. So like maybe you have situations where you have both data sources. I wonder how you combine them, if you can use, that's why I'm thinking like it should be in 2 separate phases or something. With the listwise, you have one where you train for the scores of predicting the ratings, and then you have another on top of, you know, given those, you reorder them based on what has been shown to be best, but that you can somehow use both.
Out here. So clearly, just looking at the scores doesn't answer the question that we care about. We care about the ranking of the documents. But just looking at the ordering arguably isn't perfect, because I care much more about the first 2 documents being out of order than I do the last 2. If we think of a search engine, if we put something into Google, I care much more about the first page being nicely ordered than I do about what's happening on page 50. I hope I never have to see it, so we don't mind so much. So the distance metric that is commonly used in learning to rank is called normalized discounted cumulative gain, and it takes all of this into account. So NDCG, as I'm going to call it, is a value between 0 and 1, and a 0 denotes that the list is in a terrible order. It couldn't be worse. That's a disaster. We don't want that. And a 1 is perfectly ordered. Thank you very much. So it takes into account both the order of the documents, the score of the documents, and it penalizes incorrect ordering near the top of the list more than it does near the bottom. So in order to compute this metric, we need three things. We need the predicted rank, the true rank, and the true score. And then in general, it takes that rank list and it associates a weight with each of these returned documents. So the weights are returned as this ratio. And here's an example of how we would compute it. We'd sum it up and get a distance metric. Now, in order to normalize it, we divide it by the optimal discounted cumulative gain. That is what you would have got if the list was returned in perfect order. Normalizing is really useful because it enables you to compare across different queries and across different data sets. Another thing that's really nice about NDCG is that you can truncate and get a good result. So for example, we could just say, okay, what we really care about is the top 10 items being in order. That's reasonable. So we just compute it at 10, and we'd look at the top 10 items and get that result. Okay, so I motivate the use of NDCG by saying that we don't care about the predicted scores only, we also care about the order of the returned documents too. But that pointwise linear regression method that we were using before was just predicting a score, and that's not really what we care about. We care about the order as well. So taking this idea one step further, the next class of ranking algorithms I want to talk to you about is pairwise ranking. So these capitalize on the fact that we care about the order, and they take in pairs of feature vectors and estimate which of the pair is more relevant. So the first pairwise ranking method we'll talk about is RankNet. If you care, it's a neural net, and it has many more parameters than the regression model that we saw earlier, hence it's more flexible, but that also means it's more complicated. So during training, it takes in pairs of feature vectors, and it learns a function so that the document which is more relevant is given an increased predicted score, and the one that's less relevant is given a lower score. Now, because this model training pushes relevant documents up and pushes poor documents down, RankNet is good at getting documents into the correct region of the list, but not necessarily ordering them well within that region. So, for example, it's great at ensuring that the top document is perhaps in the top 1% of items returned, but not necessarily right at the top. Furthermore, this method is working by considering pairwise error. It says, is document A more relevant than document B? If yes, we push A up and B down. And it doesn't take into account whereabouts in the ranking that is. So it would push both the top pairs and the bottom pairs by equal amounts. But earlier we said we care less about what's happening at the bottom of the list. So is there anything better that we can do? Well, yes, lambda rank does better. So lambda rank is doing the same thing as RankNet, but it scales the change in the weights and the pushing in proportion to the NDCG. So if we go back to this picture, RankNet was pushing all of these documents equally, whereas lambda rank aims to give a smaller push to the ones down the bottom because we don't care so much about those. And later we'll see that RankNet does much better than, lambda rank does much better than RankNet in practice. So the final class of algorithms that we're going to look at is listwise algorithms. So we saw pointwise, where decisions were made on an item-by-item basis. We saw pairwise, which trains itself by taking in pairs of documents and making decisions. And unsurprisingly, listwise is going to take in the whole list of documents at once. My favorite listwise algorithm is lambda-mar, and it uses decision trees to score and therefore to rank the documents. So a gentle introduction to decision trees. They're effectively a map that splits.
Okay, I'm not sure I want to do that.
Zero data. The query zero. Data function or that to be able to play around these my document decision trees. So here we see an example of one. So terribly. And you can see that as we move through the different models that we looked at to machine learning technically, the algorithm.
All right. I think that was like a good summary of the approach of learning to rank. I think like to really get an understanding of this, we probably need to spend more time, a little bit more time on those papers. Like that, it's a big topic of learning to rank, right? So trying to learn about that and then implement them, I mean, from scratch would make sense. But yeah, I think probably go back a little bit is better to try to extend this knowledge of things like incrementally. I'm not sure either. Like I'm reading this book. Let's see, like this book is great of like evaluating recommender system, but I wonder if he talks a lot about, all right, so we have introduction, we have neighborhood based, model based, content based, knowledge based, ensemble, evaluation, context. Where's like the learning to rank? Oh, advanced topics. Okay. Okay, so I guess we are learning about something complex. Maybe we should, I mean, this is probably good. It was a pretty short topic of this though. So, okay. Okay, most of the models discussed treat the recommendation problem as a prediction problem in which the squared error of the rating prediction is optimized. However, in practice, recommender systems rarely present all the ratings to the users. In practice, only the top KR items are presented. Furthermore, the user is more likely to pay attention to the items at the top. The predicted values for the items not included in the list are irrelevant from the user perspective. In many cases, optimized predicted values of the ratings may not provide the best recommendation list to the end user. For example, if all the low rank ratings are predicted very accurately, but significant errors are made on the higher ranked ratings, the result will not provide a high quality recommendation list to the end user. On the other hand, a prediction-based objective function may report as high quality solution because the low ranked items are given equal importance. This problem arises because the objective function are not fully aligned with the end user experience. So this is, what we'll be talking about. The classical objective function used in optimization models use aggregated squared error. This type of objective function is optimized to the root mean squared error measure. It is also particularly easy to optimize. This is one of the reasons such prediction-based objective functions dominate the recommendation modeling landscape. However, as discussed in Chapter 7 on evaluating recommender systems, there are many rank-centric measures used for evaluating recommender systems. Such rank-centric measures can also be directly optimized in the context of collaborative filtering. There are many I haven't read this chapter 7 on evaluating, but like NDCG, there are many rank-centric metrics. So NDCG, such rank measure can also be directly optimized. Okay, some, I guess. So you have global ranking measures, or you have top-heavy ranking measures, which are the ones that's like used. So this would be NDCG, but they are not differentiable, so that's a problem. I don't know, it doesn't say that here. Many of the ranking-based measures are used for evaluating implicit data setting. Correspondingly, many of the ranking-based learning are also designed in the context of implicit data settings. Okay. For example, consider the problem of factorizing the rating matrix R into user and item factors. One would like to determine U and V such that specific ranking objective is optimized. Then one might pose the optimization problem as follows. J, objective function quantify ranking evaluation, constraints on U and V. In the traditional matrix factorization, it is possible to add a regularizer to improve the generalization power of the objective function. The constraints of U and V might depend on the specific application setting. For example, in the implicit feedback setting, one might impose non-negative constraints. The optimization objective function might be derived from ranking-based measures such as NDCG. A specific example of such. All right, okay. The main challenge in ranking-based methods is that the underlying objective functions are often non-smooth. All right, so this is the problem with the NDCG. Otherwise, we would directly just optimize for NDCG. It can be hard to optimize with off-the-shelf gradient descent techniques. Tiny changes in the predicted ratings can change the item rankings and the corresponding objective functions suddenly. For example, consider a setting where there are two movies nearing Gladiator with true ratings 0 and 1. The predicted ratings can be converted to ranks and the top one recommended movie can be reported. The smooth is shown. All right, so you have one smooth RMSE objective. It's very nice to differentiate, and you have this where you have the prediction for the hit rate. Okay. Note the sudden jump. In the case of ranking-based objective, such non-smooth jumps or drops can occur with small changes in not just the predicted values, but also the underlying model parameters. Okay, so then the question is, one can view this approach as a pointwise methodology. These are other two primary types of methods that are specifically optimized to rank-centric learning. We have pairwise or listwise ranking methods. All right, so then we have, the pairwise where all right, so if we have, let's say we give them 3 movies where we have gotten the ratings, then we know the ordering they should be in, right? So then we have +1, -1, -1, like which pairs. We know that Alien should be less rated than Gladiator, so we give this a minus swap, or like this ordering is bad, and so on. All right, so one can generate similar pairs. For implicit feedback data sets, one can treat unobserved values as zeros. Yeah, okay, so yeah, like we don't know. One can try the relative item preferences. It's basically a binary classification problem, and the learning method implicitly tries to minimize the number of pairwise inversions in the training data. This objective is intimately related to the Kendall rank relational coefficient. Okay, so this is actually like something we can optimize, and this is what we basically have talked about a bit. But then like it's just a very quite superficial maybe here. And then we have listwise. Yeah, like we try to give it directly. These methods generally tend to be more focused on implicit feedback matrices because of the natural importance of ranking-based methods in these methods. Okay, some examples of listwise: Ko-Fi rank, Klimf, CL. Okay, I don't know. I don't know. I'm just curious, like it didn't mention ListNet, all of those that seems to be. All right, an excellent tutorial on ranking methods for recommendations may be found here. It is noteworthy that the dichotomy between prediction and ranking based also exists in classification. Okay, so let's check that out. 323. Learning to rank. That felt like really kind of superficial explanation in that book. This is kind of like it's from 2016, so this is like the most comprehensive book I've found so far on recommender systems. Okay, learning to rank, rank SVM, lambda rank, RankNet, rank boost, add a rank, ListNet. There's a bunch of them, right? Okay, so you have Pointwise, Pairwise, Listwise, overview. Okay. Pointwise, you're in a matrix factorization, SVD++, maybe some, all rating prediction methods. Pairwise, you have these BPR. Okay, and then list-wise, you have Kofi rank. Okay, that's actually maybe the first one. And then you have list rank. And then you have this CLIMF that was talked about in that paper. And then you have classification based. So there's a lot of papers to read here, I guess, of like how they work and like comparison between them. I wish someone had made like a video on this. There probably are, you just have to look for them maybe. And then you have deep learning. I mean, this is a long time ago, like in that restricted Boltzmann machines. I don't think people really use that anymore. And then contextual bandits. Yeah. All right, so you have like group recommender system. Okay, that's not. So those are like some advanced topics, I guess, learning to rank. I mean, I guess like it's, yeah, I don't know if it feels like it's really fundamental. So I don't know if I would say that it's like a advanced topic maybe, but all right, I think probably for me right now is to implement these types of models that I've sort of learned about, and then as well as the sort of ensemble or the hybrid recommender system, as well as going to this of evaluation. That seems to be like the main thing now. But all right, we did learn a lot of learning to rank. I think we got a better overview of a lot of these ideas. We understood a bit better, at least, of ListNet and maybe what to focus on next on that. But yeah, still a lot to learn. So I will probably continue on this in another stream, and I will be trying to start implementing stuff in a bit so that we can make like good tutorial videos on recommender system and build like a step-by-step playlist of like recommender systems from scratch and build some projects on that. I think will be really, really useful. All right. I think I'll end the stream here and see you next time.